Today we are going to be going through and doing the full calculation of a uh, confidence interval, and you'll see right here it's got this fancy name, one sample z interval for p, that means proportions. And we have different kinds of intervals we can create, which is why we have a specific name for this one. And hopefully, as you see the other types of intervals that you can create, this becomes less confusing for you. So anyways, we are going to look at a few of the last little bits that we need to know in order to get to that calculation and get a little bit of practice. You might expect all that. So let's start off with this. We're going to see the 10 most recent polls from Iowa in the presidential race. I picked Iowa. It's one of the closer running races right now, so I thought it'd be, I don't know, it might be more interesting. So depending on your birthday, you're going to see which particular poll you're going to be working with today. And we're going to create a margin of error and a confidence interval based on that. And you don't know how to do that yet. You might if you read the chapter and you feel comfortable with it. But assuming you haven't done all that, you don't really know what you're doing yet. So all you need to do is copy down the relevant data. And we will go through and you will be able to calculate your confidence interval from there. Now we're going to specifically be finding the confidence interval for Trump's vote share. So we can just jump to the table now. You can find your birthday, month, and copy down the relevant data. So if your birthday's in January or February, then all we're interested in is a confidence interval for Trump's vote share, which is right here. So you really don't need Biden's number. I just threw it in there to show that these are the poll numbers, but we're going to be working in, yeah, there we go. I see someone who's lived in Iowa before, so there we go. Now you can find out what's going on in your old stomping grounds, politically speaking. All right, and you just need to copy this down. You're going to need a sheet of paper with you today. You're not going to be writing too much down, but you can copy that. So again, right now, you're not actually constructing anything with this. You just need to have those numbers. And specifically, you're going to need whatever's in this column, and you just need to write down two numbers. So I'm just stalling a little bit, but I'm assuming everyone's good to go, so I'm going to move forward now. Okay, so this is what we looked at yesterday at the very end of the day. We were just kind of throwing out the concept that a confidence interval is basically your point estimate plus or minus a margin of error. Now, the number that you wrote down for Trump's vote share, that's our point estimate. We already have that. That's the easy part of this. And the margin of error, I don't want to say it's hard, but that's what we have to work on today. We're going to find the values we need to find the margin of error, which is a critical value and a standard error of the statistic. And we'll go through what both of those are and calculate those. And there we go. So we're mainly focused on the margin of error. So we're going to start by going back to sampling distributions, and hopefully this looks familiar to you. What you have here is the standard deviation of a sampling distribution of proportions. So this is on the AP formula sheet. I think I copied it from there, and you've seen this before. Now this is fantastic, but it assumes that we know the true population proportion, P. We don't know it. So our best guess is the sample proportion that we obtain. So depending on the number you wrote down for Trump, anywhere, whatever that number happened to be. So 40-something%. Okay, that's our best guess according to that one sample. And so what we've got here is, you're going to notice not much has changed, but what we have here is we're not working with the standard deviation of the sampling distribution. What we are creating is what's called the standard error. You see it's this S like we use for standard deviation for a sample, but we specifically call it the standard error. It's important to understand that terminology. Okay, the only change between these two, which should stand out really clearly, is that we're using the sample proportion instead of the population proportion. So again, not really much, that you have to wrap your head around with this, except that this is not a standard deviation. That's going to be the the biggest conceptual leap for you is that this is not the standard deviation for the sampling distribution. So I want you to go ahead and write that formula down, and I'll give you a few seconds to do that. And I'm assuming you guys have had time to copy that formula down. Stalling just a little bit. And now we're going to move forward. So yeah, make sure you have this formula written down to go along with your calculation. And what you're about to do is construct a standard error and construct a model of your distribution. Now this is maybe a misnomer right here, a model of your distribution, but we're using that in a certain sense. So here's an example. If Trump's vote share was 44% and 780 people were included in the poll, then the calculation would be, well, when I don't have the generic formula, but my p hat is 0.44, 1 minus p hat is 0.56, 780 is in. Just run that through the calculator. I get a standard error of 0.0178. The mean, not the mean, it's the p hat, which is the mean of our distribution, is 0.44. And so this 0.0178 is kind of like the standard deviation of this. It's not a perfect correlation, but it's going to serve for our purposes for now. So go ahead and take a minute or two to do that. And hey, what do you see? A caveat right there. We are not looking at a sampling distribution when we make that. We are looking at a point estimator, but it's going to help when we get to the next step of this, because what we just found is a sampling error. I'm not going to go back to the slide, but remember, we need the sampling error of our statistic and we need the critical value. So when we get to the critical value, it's going to be helpful to think about this as a distribution. Okay, and this is just restating what I just said. So what is the critical value? Well, so glad you asked. Let's jump into that. We are going to first of all look at the empirical rule. And so you can remember the empirical rule, the 68, 95, 99.7 rule, which has worked really well for us. And you can see right there what it's referring to. 95% fall within 2 standard deviations. Good rule to have, except it's also incorrect. It's close enough for our purposes, everything we've done so far. But here's how the data truly falls in a normal distribution. And again, you could derive this using calculus if you wanted to do a calculus-based statistics course one day. But what you can see is that it's not exactly 68%. It's 68.2% within 1 standard deviation, 95.4% within 2 standard deviations, and then 99.7 within 3 standard deviations. Now, the reason that's important, and I'll just illustrate it right here, but we'll go through the process a little more in a second, is if I wanted to find a 95% confidence level, what that means is I want to find from my p hat, I would want to find where 95% of the middle most likely outcomes would be. So I can think of it like a distribution, a normal distribution, and I want to go out 95%. Now, it'd be great if it was right at 2 standard deviations, 2, in this case, standard errors away, because then I could just say, oh, what's my standard error? S sub p hat. Oh, I'll just multiply that times 2. So 2 times that will give me 95%, but it's not exactly 2. It's close to 2, but it's not exactly. Okay, so our critical value is what we're going to be using to tell us how many standard errors should we go to capture 95% of the data, or whatever our confidence level is, 90% of the data. And those are, of course, the most common, 99% of the data, and so on. So anyways, this is going to be kind of our scale factor to say, take your standard error and move out a certain distance away to create your interval. And you'll notice that, and well, you aren't seeing the critical values yet, but the critical values get bigger depending on your confidence level. So 99% is going to have a bigger confidence, a bigger critical value. And so that means this would have to be widened out and therefore creating a bigger confidence interval. All right, so that kind of explains why our confidence level is directly related to that confidence interval width. So that's kind of the heads up. So anyways, I kind of ran through how that's going to be important for confidence intervals, but just keep in mind that 95% is not going to be 2 standard errors away. It's going to be close to it. All right, so the number of standard errors that we want to move away from the point in order to correspond to the confidence level, that's our critical value. And we call it Z star, which is not the same as a Z-score. I'll interchangeably call it Z-star or critical value, though it might be better if I call it critical value every time. But just be aware you can call it that. It is not the same as a Z-score. It is the distance away. It's very similar. So Z-score is how many standard deviations of values from the mean in a normal distribution, and Z-star tells us how many standard errors to go out to create a confidence interval with a specific confidence level. All right, so where do we find these? In your AP formula sheet. You can find, as you scroll through it, and you don't have to do this right now, but you can see table B. It's a T table, and we're going to use a T table tomorrow, but it's a T distribution of critical values, and we're specifically going to focus on the very bottom of it. Notice, nice and convenient, it says confidence level, and it gives you all these different confidence levels. The most common right here in the middle, and for 95%, our just the very bottom row here, next to the infinity, you can see 1.96. And yeah, we'll talk about what the infinity means tomorrow. But 1.96, we said it'd be close to 2, but not quite right at 2. So 1.96, you will always use this for your 95% confidence level. For proportions, I should add. There are different values you will use when we get to means. That's going to be something we talk about tomorrow. 99% right here, 2.576 is your critical value. 90%, 1.645. The 80% is used sometimes, 1.282. So where do these critical values come from? So now let's go back to this and think of the model. I just had you sketch it. It didn't have to be super fancy or accurate when you did this, but at the middle of your model that you created, you had your p hat. And of course you had your standard error that went out. In my case, my birthday happens to be February, so I did the first one. Some of you might have already done this one, so you can double check. I got 0.024 as my standard error. Yours should be somewhere in that range. If you got something wildly different, you can double check your calculations. So when I say in that range, it should be just a few percent. Okay. My p hat was 0.48. That's not subscript. I just am putting the number over there. So anyways, if I want to create an interval that has 99% confidence, let's say, then of course I'm going out, and we already talked about this, I want to go out 2.576 times the standard error in order to capture and create that confidence interval. So if I think about this as the normal model, then 2.576 standard errors, there's 1, 2.5, so somewhere around here. That far over, and I'll just do equivalent on the other side. And this, you can see, is most of the area underneath. And that's 99%. So how far did I move above and below my mean, which is the p hat? Well, this, and we've done something like this before. I can take that 0.99 and I can divide it by 2, which gives me 0.495. So knowing that the mean is sitting at the 0.5 level, this is the 50th percentile right here in the middle, then I can go up 0.495 from there. So that's going to be 0.995 at the high end. Actually, maybe I should put it right here, 0.995, because I just did this 0.5 plus 0.495. And I can do 0.5 minus 0.495 to give me 0.005 right here. Now, why do we go there? Well, now if I figure out here's my upper area, here's the lower area, and I subtract those, 0.995 minus 0.005, that gives me 0.99. That's the 99% of the area falls between that. Now, I should be careful when I talk about this. I wrote this as though this is the z-score or the critical value. It's not. This is the area that falls underneath this line right here. So 99.5% of the area is underneath this line, all this shaded area, including this area underneath here. Only 0.5% of the area falls under this value right here. So I was taking the 99.5% of the area, subtracting the 0.5% of the area, and getting 99% of the area. So the reason for kind of looking through this, and you don't have to reason through it this way every single time, because you have this table with your critical values, but it's important to understand where they come from. So if I want to figure out what that critical value will be, I want to do an inverse norm calculation. So I'm just going to do this. I know that my upper area is 0.995, so I want to do inverse norm of 0.995, 0 and 1. And if I do that, and I encourage you guys to do the same thing on your calculator, then I get a z-score of 2.576. And if you look at that, that's the z-score that's the critical value. So the z-score and the critical value are very similar, but the terminology means something very different, even though in practice it's the same calculations. All right. So if I did another example here, let's say I was only doing the 80th percentile. Okay, so half of 80%, I'm looking for the middle 80% of the data. And some of you with the TI Nspire, you can actually just put middle as one of your parameters when you're on the interface. And you can make this a lot easier. Just put 0.8 and middle, and it'll tell you the stuff anyway. So you have an advantage. But for those of us with the yellow TI-84s, I want to take the 0.8, divide by 2, which gives me 0.4. I want to take that 0.4 and add it to the middle. So 0.5 plus 0.4 gives me 0.9. So 90% of the area is going to fall below that highest value. So I'm going to inverse norm with 0.9 as my area. And that gives me 1.282, which is sure enough the critical value. So just to wrap this up conceptually, and if I'm going too fast and you need me to explain this again, we can. But just to wrap this up conceptually, the critical value is saying how many standard errors we need to go out from our p hat in order to capture 80%, 90%, whatever our confidence level is, 95% of all plausible values. And so I'm going to move out in both directions, 1.96 standard errors, and then that's going to capture 95% of all plausible values. Not all of them, and so there's still a 5% chance that our true value is outside of this range. And I hate to say 5% probability, but there is a, we are 5% confident that we didn't get it right, if you want to think of it that way. Okay, I will stop there explaining it. If you have questions, you can let me know, but I'm about to move ahead. Any questions there? Okay. So what I want you guys to do is just fill this table in. Notice that we got 3 different scenarios going on, and I want you to figure out what critical value we need to use for each one of these scenarios. And once you've got it, you can just write it in the blank. So I did intentionally throw in all of the information, and this would be all the information you need to create a confidence interval. But I did intentionally make these p-hats ones that were similar to confidence levels. But keep in mind, for our critical value, the only thing that matters is this column right here. So for this question, none of these values matter at all. We just look at these. And then we compare it to table B, or well, it is table B, but the critical values, the confidence levels. Anyways, so there's 95%, here's 99%, and here's 90%. Okay, so that is it. I'm assuming that sounds pretty straightforward now, but are there any questions on that? Okay, so now you know what a critical value is and you know how to find it, and you'll want to refer to that table B. In fact, I'm going to pause right here and I'm going to share this real quick just so we can see the AP formula sheet. So everything we did first semester, I don't even know, time is an illusion at this point, but all of the stuff we did up through the break really is captured in these right here, which means it seems like we didn't do a lot because there's a whole heck of a lot of stuff that we still haven't talked about. Luckily, these are things that once we start learning them, they kind of all flow together. So today we're looking at proportions. You can see right here, here are your proportions. This table down here is for means. This table right here is for linear regression. And we're going to get to all that stuff later. So for today only, we got proportions. And here's our sampling distributions, but we're not dealing with that. We're looking at the standard error. So this tells you the formula for the standard error of all your statistics. So here's the standard error for one population, one p-hat. When we get to a difference of proportions, we can do that a different way. So we have the same stuff for means, and it gives us our confidence interval basic formula. And then as you're looking down, here's table A, which is your Z table. And then here's table B, and the very bottom of it shows your critical values for proportions. And those are all at the very bottom of this. So I highly encourage you guys to get familiar with this formula sheet. And all the information you need is on here. You might have to just skip around a little bit to find it all. Okay, now let me go back to our other. Okay, so this is what we've got. We worked our way from the kind of basic formula, and we're going to substitute some stuff in. So now our specific formula is that it's p-hat, which is our statistic, plus or minus z star, which is our critical value. It's important to know that there are other critical values you could use. We're going to learn about t star tomorrow. And standard error is right here. This is specific for proportions, one proportion. So I just substituted that in. And this is what we call the one sample z interval for proportions, or it's also called a one proportion z interval. The actual name here doesn't matter. If you can get this point across, the z interval, it's important to show that because you can also create a t interval. So it's important to know that you're using z-score, a z critical value. And we can find the margin of error with the following, which is really just the second half of this equation. So there you go. That's your margin of error. That's where this all comes down to, and it's summarized up like that. So now what I want you to do, okay, I want you to just calculate your margin of error and confidence interval for the polling data I gave you at the beginning of class. And of course, before you can do that, I didn't give you what confidence level we're working with, which you'll need to know. That is going to be a 95% confidence level. And if you need to see the critical values there, I'll go back. But just, I'll go back real quick so you can find the critical value you need. Okay, so there's your critical values. Find the one that's relevant for this particular problem. Okay, hopefully you're finding that pretty quickly. You can chat if you still need more time. I'll chat back at you what you should be using. So now I will leave you to calculating the rest of it from here. So without saying specific answers, I will just generally let you know your confidence interval should be something like 0.4 something, whatever that is, dot, 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 to 0.5 something, dot, dot, dot. So if you got really different answers from that, then you did something wrong in your calculation. But yeah, you can kind of just, and it might be a little higher or lower than the 0.4 or 0.5, but anyways, that is it. That's your confidence interval, and you've calculated one. Hopefully you guys are feeling good about that. I'm ready to move forward unless you guys need some more time.
I'm good. You can go forward.
Okay, thank you. So here is the other type of thing that can happen. And it's important to go through a couple of these types of problems. This is not wanting to erase, so. All right, just a second. Okay, so when we are looking at this, I'm only focused on the margin of error, but notice another type of problem that we can answer with this. So we want to create a 95% confidence interval for a proportion of voters who prefer Biden, but we don't want a margin of error greater than 3%. So how many people should we sample in order to make sure that we don't have a margin of error greater than 3%? Well, we can calculate that. We are just going to substitute numbers that we know. So my margin of error needs to be 3%. So I'm going to put that in as margin of error 0.03. I'm actually going to move this over. 0.03. Now, my z-score, because it's a 95% confidence level, is going to be 1.96. And it's the square root of what I don't know for sure is the n, but also it doesn't tell me the p hat right here. So in a situation like this, and you kind of have to use your own intuition here, in a situation like this, we don't know if Biden's at 43%, 51%, something like that. So it's just fair to go with a 50-50. So if you don't know, then you could just say, okay, I'm just going to assume it's 0.5. And so 1 minus that is going to still be 0.5, because this is also going to give us our biggest denominator. And our biggest denominator means that it is going to be the largest denominator required. So if that makes sense, the bigger the numerator is, the bigger our denominator is going to be. So it's a more conservative estimate to say 50%. Okay, so maybe we're going to pull more than we needed, but it's better to be conservative in this case. All right, so now we've got our numbers filled in. We can just do some algebra. And it's important to remember that these two expressions are equivalent. All right, so I didn't change much there, but now I separated the square root. And now I'm going to do kind of two moves in one here. And I know you guys could figure this out algebraically. I'm just going to run through it. So if I want to move the n over to the other side, the square root of n, I'm going to multiply both sides by square root of n, but then I want to move this 0.03 over, so I'm going to divide both sides by 0.03. In essence, what I'm doing is just doing a switcheroo between these two. So those two can change places, and I end up with the square root of n equals 1.96 times the square root of 0.5 times 0.5 all over 0.03. And now I can just do that calculation and come up with the square root of n. All right. And that's what I got as my answer. Again, I know I'm kind of jumping ahead. Maybe some of you are spending a little more time doing this calculation. I don't know. But just under 33. But that is the square root of n. So remember, to get n, which is a sample size, we're going to need to square both of those. All right, and I got 1 repeating for my decimal right there. If you got lost in any of this algebra, you can stick around later. We can go through it. But this is hopefully nothing that you're getting too lost in. So keep in mind, we want to make sure that our margin of error is no greater than 3%. If I round down right here to 1067, then I know it doesn't sound like much, but then theoretically our margin of error will be greater than 3% because we didn't have quite enough people. So we always want to round up. So even right here, when I have 1/9 of a person left over, I'm going to round that up. And so this is going to become 1,068 people that need to be in the sample. And this will guarantee that my margin of error is no greater than 3%. Now it could be a little off because I estimated what p hat is, but whatever p hat is, it's gonna, be less. I'm gonna have less than a 3% margin of error by using that many people in my survey. Okay, so we're gonna go through one more example of this. And I think this next example, it's the same thing, but the next example will kind of show a little bit more as far as the polling process. And anyway, so we're estimating right now that 35% of all people are registered Democrats. And we're going to conduct a survey that it'll ask a lot of questions, but one of them is finding out if a person is a registered Democrat. How many people should be in the survey if we want a 99% confidence interval to have a margin of error of 2%? All right, so the same thing as before. My margin of error is 2%. I'm going to start with 0.02. The critical value, it's a 99% confidence interval. So 99% was 2.576 for the critical value. Now it's the square root of p hat right here. Now this is an estimate that it's 35%. This isn't coming from a national database or anything. So I'm going to assume that's 35%, and 1 minus that is 65%, all over n. So saving a little bit of time, I'm just going to do that switcheroo real quick. So now I end up with the square root of n equals 2.576. And that, let me do this a little differently. That's going to be 0.35 times 0.65 all over 0.02. When I do this, well, we'll just put the answers up in a second. You can do that. Okay. So 61.434. I believe that's correct. I know it's in the right ballpark. So that is a square root. So when I square that, it's showing me that I need 3,774.0976 people, which I'm going to round that up to 3,975 people. So the purpose of this question is twofold. One of them is to give you more practice with figuring out what your sample size should be if you want a specific margin of error. The other part is to show why our margins of error tend to be around 4%, because it's there's an inverse relationship, of course, with the margin of error and the sample size. And a margin of error of 4% is about 1,000 people, okay? Now that can change, but I mean, it's kind of fair to say about 1,000 people, depends on what confidence level and what the p-hat is. But we have to almost quadruple that to reduce this by a factor of 2, or a factor of 1/2. So you'll see why the margin of errors tend to hover around these higher values, because getting it down to 2% requires a heck of a lot of people, okay? Now we could have changed that with this 99%. If I had changed that to a 90% confidence level, I wouldn't have to get as many people in the survey. If I knew the p-hat was a little closer to 0.5, if it was like 0.45 instead, then that would require fewer people as well. Or actually that would require more. I'm doing my math wrong. So if it went down, if it was like 0.25, then that would require fewer people. So I don't want to spend too much time on this, but you need to kind of be familiar with how all these different levers factor into the sample size required. Okay. So we're going to wrap this up. We do need to meet certain criteria, and I'll tell you that we met these conditions already with everything we've done so far, but these should look familiar to you. We have 3 conditions that need to be met. First of all, the sample that you're collecting, that you're getting your p-hat from, must be a random sample. If it's not, then a confidence interval can't do anything to fix that. You must meet the 10% condition. This allows us to use the simpler calculations like we're using, and these are the simple calculations. So if it was more than 10%, then we'd have to factor in, the without replacement. We might have to use different calculations to get a better estimate. And the large counts is our way of finding out, is this a normal distribution that we're dealing with? And so that's where your n times p and n times 1 minus p must both be greater than 10. So those 3 conditions are not new, and these are going to be kind of standard conditions. I will tell you the large counts only matters whenever we are dealing with proportions. And we have different stuff for means, which we'll talk about tomorrow. So we're going to go through one practice problem, then call that good for the day. I will leave another practice problem that's almost identical to it. I mean, the prompt changes, but the rest of it's the same. I'll leave that for you guys to work on as part of your homework tonight. So here's what we've got. We've got 34 of 85 people in a recent random sample of FHS students said they prefer remote learning. Construct a 96% confidence interval for the proportion of FHS students that prefer remote learning. Okay, 96%, that is a weird one. Now you can go back to your table B if you can pull that up. In fact, let's just do that real quick. We could calculate it on the calculator, but I'm going to go over to this. And we're going to find what this critical value should be. Here's table B, it's a T table. And 96% right here, 2.054. All right, so we're good with that. Let me go back. All right, and here's kind of the process to answer this. If this was an FRQ and you wanted to give a very complete response, this is what we'd want to do. We'd first of all want to state the parameter that we're going to estimate. We want to find the true proportion, or estimate the true proportion of FHS students that prefer remote learning. And that's my parameter, true proportion of FHS students that prefer remote learning. Okay, that's what we're trying to estimate. And our confidence level is 96%. And just for our purposes right now, we saw that that has a critical value of 2.054. Okay, so now our plan is we want to identify the appropriate inference method and check conditions. So this is maybe the first time we've talked about it, but here's what this inference method, what that was referring to. We are working with a sample and we want to infer something about the population from that. So that's where inference comes from. So we're only working with a sample. We're going to make a claim about the population based on our statistical methods, but we have to pick the right way of calculating it. We only know one right now, so we don't have anything to pick from. But later, of course, you'll have a few other inference methods you could pick from, so you have to pick the right one. And we'll check the conditions. So the name of our procedure right here is a one sample Z interval for P. That is the population proportion. The conditions, we need it to be random. We need it to be 10% met. And we need it to be normal, which in our case is large counts condition. So put LC right there. So is it random? Well, it says right here, this is a random sample of FHS students. So yes, it's random. 10%. We had 85 people in this survey. And the question is 85 less than or equal to 1/10 of the population? So I'll just put FHS right here. Well, there's about 1,700 students at FHS, I mean, plus or minus, but it doesn't matter a great deal. So 1/10 is 170. We're definitely below that. So we're good on this count. And then the large counts. So I can do the 85, and we need to figure out what our P is, what our, it's really P hat, but what our sample proportion is. It's going to be 34 out of 85, which is, happens to be exactly 0.4. And I'll tell you, when I created these numbers, I just picked random numbers. It just happened to work out this way. So N times P and N times 1 minus P have to both be greater than or equal to 10. And that's going to be 85 times 0.4, and then 85 times 0.6. So when we do both of those, of course, 85 times 0.4 is what we started with. It's 34 times 0.6 is 51. You can do that math real quick on your own just to verify it, but we meet the large counts condition. So we've met all three conditions. We can proceed. Okay, so we started off with stating the parameters and the confidence level. Then we planned out what we're doing. We're going to pick this inference method, and we're going to check these conditions to make sure we can move forward. We've done that. Now is the do part of this. We want to actually do the calculations. And just to give a complete answer, we want to show that we have a very thorough understanding. We want to give the general formula for any confidence interval, which is going to be our statistic plus or minus the critical value. So that's, you can't really read my writing very well, but that says crit value times the standard error. All right, and I just pulled that straight from the formula sheet. That's the general formula. And now we want to kind of get more specific. Our specific formula here is going to be P hat plus or minus Z star. And again, it's important to identify that Z star is your critical value, because we do have other critical values we can use. And I think I've already said that, but I'm saying it again. The standard error is going to be the square root of P times 1 minus P all over N. And now we have thoroughly shown that we know what we're doing. And now we're ready to go ahead and do the calculations. I'm going to start plugging in. This right here up at the top is P hat. So it's going to be 0.4 plus or minus. My critical value, we already found that right here, is 2.054. And remember, on your AP test, you're going to have access to all the critical values you need. On your calculator, you can do that more, but they're not going to give you anything that's not on the formula sheet. So they're not going to give you like a 91% confidence interval. Okay, this standard error is square root of 0.4, and then 1 minus p is 0.6. N is right here, that's 85. So you guys can go through and calculate that. I'll just show what it is. I'll show the final answer also, but I'm just going to first of all calculate the margin of error. So I put the margin of error up there. You don't have to look at it right now if you're doing the calculations on your own. Okay, and when you guys are done with your own calculations, you can compare what you got to what I got up here. And if I did anything wrong, you can point that out. So this is not a final answer. I might have just said final answer a second ago. This is not our final answer, because if you left it like that, you haven't really put it back into the proper context. So the last little bit you want to do is the conclusion. You want to interpret your interval in the context of the problem. And I gave you a template for this yesterday. I think my goal tomorrow is going to be going through how to do stuff for means. And then Monday, the day before the test, I really want to just go through and hammer home like the proper way of answering this, but this is kind of the process. So we can just start it off as we are. Now you say we are, it's really I am, but we are makes it sound like it's more official or something. We are 96% confident that the interval from, this is where you write your interval, from, we could say 29.1%. You could just put it as 0.291. It's not a problem leaving it as a decimal. From 29.1% to 50.9% captures the true proportion of, and now we add the context of FHS students who prefer remote learning. Okay. So I wish I had added one extra question onto this, and but I'll just kind of verbalize this question instead. So suppose someone said, oh, 34 of 85 people in the survey, oh, well, therefore, a majority of people don't want to stick with remote learning. And the question is, can we definitively say that a majority of people don't want to stick with remote learning? And just the takeaway from this, looking at our confidence interval, at a 96% confidence level, we cannot rule out the fact that a majority want to, because look, we go from 29.1% to 50.9%. We cross that 50% barrier. And so therefore, theoretically, there could be a majority of people who actually prefer online remote learning. I made these numbers up, so it's not based on anything, but according to this made up survey, there could still theoretically be a majority of FHS students who prefer remote learning. All right, because it's within the 96% confidence interval. All right, so that's kind of one takeaway from this. And if that doesn't make sense, maybe you can stick around, we can ask some questions. So what I suggest to you, if this is something that you find helpful, go ahead, take a screenshot of what I've just done here with your iPad. If you don't think you need it, you'll be able to come back and look at this without the work done. But if you want to see the work done for this particular problem, I'll give you a few seconds to take a screenshot of it. Because the next page has another problem, we are not going to do that. So I'm going to go ahead and delete. I'm assuming everyone has had time to take a screenshot if you were interested in doing it. Okay, and the next page, it's more of the same. So everything from the 1 through 4 down is the same. It's a different context. So I encourage you guys to do this as part of your homework. It's not going to be the one that you turn in, but it's really important that you get practice going through this full process, answering it as though it's an FRQ that you need to give a very thorough response to. So you can use the previous answer as your template for that. And with that, here's your homework for tonight. You need to read, you're only going to read part of chapter 23 because that's what we're going to be talking about tomorrow. Your homework right here, the only thing to mention is that for problem 21, you're going to need to go back and refer to the chapter, page 447, to get part of the context you need. And we're going to do chapter 23 tomorrow. If you guys are feeling comfortable with everything we talked about today, you can get to doing that. You can head out. But if you have any questions, you can feel free to stick around. And with that, I'll just say have a wonderful day.